Okay, so today we're going to talk about inner product and norm, and then the idea of projection. And I'm hoping, and then contrary to what I mentioned last time, we're going to try to cover the all the linear algebra today. So no third lecture, hopefully. And how fast we move. So then by next week we're going to talk about something else, but probability, and then we'll have the preliminary. So the first thing to talk about is the idea of inner product. So how many people have seen inner product in your algebra? So what is an inner product? Let's go. Yes.
Show that it's starting.
Anyone managed to? No? I'm gonna tell you what inner product is in just a time. So inner products for any two vectors, x and y in Rn. You can define an inner product, which is a scalar, and just if you have coordinates. So let's say if I represents the vectors like as column matrices, like column vectors, or like an n by one matrix, then you can think of it as y is also like this. So the inner product is just multiply each coordinate and then sum, which is also equivalent to doing like x transpose times y. Okay, so this is matrix multiplication. X transpose would be 1 by m. And then this would be n by 1. And so you would get this x transpose y. We also use this notation, which is common. It's like bracket. Use brackets to denote the inner product of two ways. Okay. So hopefully this is clear. And a little bit more. Right. So any questions about this? So it kind of has something to do with the norm and the angle. And so, for example, you can define a norm. So the inner product of a vector itself is going to be well defined. It would be a number. And so what I can do is form this inner product and then take the square root. And this defines the norm of a vector. Okay, so if you have like R2, this matches what you imagine a norm would do. So if you have a vector, let's say 1, 2, so the length of this would be only the length of this. Like Pythagoras. Anyone? How do you calculate the length of? Yes.
So b2 squared plus 1 squared, b2 squared of that, so square root of 5.
Yeah, I assume that I heard something like this. One to like the first coordinate squared plus the second coordinate squared. That would be like these two, right? The squares of these are basically this part. So if you look at it, a triangle, 1 squared plus 2 squared, and then you take the square root, which will be root 5, and you can see this is just really the norm. So if this was x, this is the norm of x, which is just gives you the length of the vector. Okay, so that's matches your intuition in 1 and 2 and 3 dimensions, and then this is like a generalization of length of a vector. And so if I have the length, then I can define the distance. So if you imagine if you have two vectors, x and y, then if you take the difference of two vectors, hopefully you would see, you've seen this. So y minus x would be something like that, right? So this is x. So we have x and then plus y minus x gives me y. So that's the vector addition in picture. And so the difference, the length of the difference, you can see gives me something about the distance of the points. So if you look at the norm of y minus x, that will be this distance. Okay, and you can think of vectors x and y as also points. So rather than vectors, I can just look at the endpoint and think of the vector. So this you can think of it as a vector or really a point. I mean, mathematically, it's more of a point. I mean, it depends on what perspective you take, but you can either view it as some like an arrow from 0 to this point or just a point in R2. For us, mostly it's just a point. So x is this point, and y is this point, and then the difference, vector difference of y minus x, the norm would give you the distance. It's like natural. But the length of that vector is the distance. So you can define the distance of two vectors as the norm of the difference. Yeah. So the distance between point x and point y in Rn would be the norm of the difference, which is just, if you write it in terms of coordinates, would be square root of summation xi minus yi squared. Okay? Any questions? So this allows you, in general, if you have, I mean, it can be a little more abstract, you find a linear product a little more generally. Once you have a linear product, you have a norm, a notion of length. And once you have a notion of length, you have a notion of distance. Linear vectors. Yeah. So you can measure distances, you can measure norms, and also you can measure angles. Anyone knows, I'm not going to spend too much time on it, but anyone knows like how do you find an angle? Angle between two. Yes.
Input is going to be the norm of each of these vectors times the cosine of angle.
Right. Okay. So in other words, the cosine of the angle between two vectors would be the inner product. So let's say theta is the angle between, I'm going to write it like this, between x and y. So the angle between x and y will be the inner product divided by the norm, the product of the norms. Okay. There's an inequality in math called Cauchy-Schwarz that guarantees that this is going to stay between -1 and 1. So it's really can be the cosine of something, and that something would be the angle. Okay, so that would be, for example, in this case, if this is theta, then that theta, the cosine of it, you can measure like this. And so you can also do the angle. In other words, like the inverse of the cosine, arc cosine of this quantity would be the angle. So we have the angles, we have the distance. So everything follows from the inner product. The inner product gives you norms and distances and angles, like defines a lot of geometry. Have people seen this? Okay. Good. Any questions? Go back. Oh, great. So if you have a notion of an angle, then you have a notion of orthogonality. So you can say two vectors are orthogonal. When do we say two things are orthogonal? When is it true that two vectors or anyone? Are these two vectors on top orthogonal, X and Y? They're not. So can you give me an example of two orthogonal vectors? 1,
1, 0, and 0.
okay, 1, 0, and 0, 1. These two. So these two vectors are orthogonal. Another way to say it is that the angle between them is 90 degrees. So if I have the angle, I can define orthogonality. So I'm going to say two vectors are orthogonal if the angle between them is 90 degrees. What is the cosine of 90 degrees? Try to cosine of 90. 0. Okay, so once I have the angle, I kind of intuitively know that the angle being 90 is something that we call orthogonal. So I can measure it. So if I plug 90 here, or plug over 2 will be 0. So x and y are orthogonal. If and only if, or define, we can define it like this, depending on how you define it. But if and only if the angle is 0, which is equivalent if and only if the inner product is 0. Because like the fraction is 0 if the numerator is 0. So two vectors are orthogonal if the inner product is 0. It doesn't matter how large they are. For example, this one is also going to be orthogonal to anything in this direction. The length of the second one is different, but the direction is the same. So as long as they're 0. So you can verify. This is really easy. So it's like inner product of 1, 0 and 0, 1. It's just 1 times 0 plus 0 times 1, which is 0. So algebraically, you can see it. You can argue by the angle and so on. So this notion of orthogonality is important, and this is kind of our notation. Okay, yes.
Pull the second angle next.
Yes, yes. The angle should be like, let's do pi over 2. Great, thank you. Good. Okay. Oh, I forgot. There's an exercise that you can do. This is going to be useful for us. If you square this norm, you can write it as norm of x squared plus norm of y squared minus 2x inner product y. This is like the usual. It's like a plus b squared is a squared plus b squared minus 2ab. But for vectors, and this can be done by writing this as an inner product of x minus y with itself, like this transpose that you can use it as a matrix multiplication, and then just expand and then cancel things out. So doing it as an exercise is very useful later on, potentially. Okay, that was an aside. So we define what it means for x to be orthogonal to y, which is denoted again via this notation. And it's defined, we can define it as equivalent to x and y having inner product 0. Now what I want to do is define what it means for a vector to be orthogonal to a subspace, a linear subspace. Okay, and the natural thing is to define like this. So if V is a linear subspace for a linear subspace V, subset of Rn, so they are in Rn. If you pick another vector in R and X, you say that X is perp or perpendicular or orthogonal to V. If X is perpendicular to every vector in V. So X is perpendicular to little v for all V in capital V. Okay, so the vector is orthogonal to a subspace if it's orthogonal to every vector in the subspace. Okay, here's an example. Suppose we have, say I have, what I have? Say this is z-axis, this is x-axis, this is y-axis, and let's say you have a plane here. This is a plane. So can you give me an example of a vector which is orthogonal? So this is a subspace. So V is the set of all vectors, let's say alpha, beta, 0, such that alpha and beta are in R. So this is the xy plane in R3. So this is a subspace of R3. Can you give me an example of a vector which is orthogonal?
Is it just one that's pointing straight up?
Yes. So it's not just one, but that's an example. So for example, any vector that's in this direction. So for example, like 0, 0, 1, that would be an example. Another one would be like, I don't know, 0, 0, 3. Anything in this direction would go orthogonal. Is it clear? So the reason is if I pick another vector here, let's say I pick something like this, or something like that, or something like this. The angle between this vector and any one of these vectors is going to be 90. Or like it's easy to see because algebraically, it's like if you look at, for example, this one and any vector here, if you take the inner product, 0 times alpha is 0 times beta plus 1 times 0 would be 0. So it doesn't matter what alpha and beta are. Okay? It's always going to be 0. So, like, that's why it's called linear algebra, because you can argue about geometry using algebra. Okay? So, you take the inner product, the algebraic inner product. It would be 0. Like, intuitively, it also matches our intuition that this vector is off the channel in the variable. So, okay. Sounds good. Can you find any other vector? Is there anything in this direction that's orthogonal? Yes.
There's one that points down.
Yeah, okay, so that's true. But that I would say it's also considered in this direction. So I mean by direction I mean this entire line. Okay. So that's still in this direction, but like negative. Yes. Anything else?
This might be stupid, but are we assuming that the vectors originate at the origin? Like, if it's a plane, right, then like a vector that's like on 1, 1 on like the x, y and still pointing up, that'd be orthogonal, right? Or
One, what do you mean by 1, 1?
like if it were just like somewhere else on the plane and then pointing straight up. That'd be
Oh, you mean
orthogonal.
starting from here and then pointing out?
Yeah.
Okay, so no, yeah. So what we do is like, it's a very good question, and it's an interesting question to think about. But like vectors for us are the points or arrows starting from origin to that point. They're not gonna originate anywhere else. So this viewpoint is going to be a little bit confusing at some point, but when we do arrows, we always start at origin. Really, what carries the information is the endpoint. Yeah. So either arrows that start at origin and end at what we want, or just points at the end, depending on the so given that, is there any other vector that is orthogonal? You want to start from the origin, go in any direction, and then think about the arrow relations with these. Any arrows that end here. If we have any other thing orthogonal. Yeah.
Maybe the 0 vector?
Okay. You're finding all the corner cases. Right. So 0 is also trivially orthogonal to anything. But technically it's like in every direction. So yes. Good. 0 is also orthogonal. What else? Anything in this direction, positive or negative, as well as 0. Yes.
Fourth dimensional vector.
Okay, so we have to be restricted to the ambient dimensions. Ambient dimensions are true. So I gather that there is no other one because we're like hitting like the walls of the space. So if you stay in the space, there's no other thing. So every vector that's orthogonal to xy plane is on this line or like in this direction. Okay. So this gives us the notion of orthogonal complement. So if I gather all the vectors, V in our like Rn, such that V is orthogonal to, or sorry, let's do X, any X that is orthogonal to V. So in this case, this happens to be just the Z-axis. So the 0, 0, that's a gamma, gamma in R. So this is a useful notion. And so all the vectors that are orthogonal to a subspace gives me a different subspace, which we call orthogonal complement, V per. For every subspace, there exists a complementary subspace or orthogonal complement that gives me all the vectors that are orthogonal to V. And in this case, it would be the Z-axis. Okay. So if you have two subspaces, one is the XY, then this is going to be also a subspace. It's going to be a linear subspace. Both of them are linear subspaces. So this in this case would be one-dimensional, would be this entire line. And this is orthogonal to V, and everything that's orthogonal to all the vectors live in this space. So that's the orthogonal complement. Does that make sense? Yeah.
Just a little off topic, but V exists in like the XY plane, right? It like exists in the third dimension, but like it's not adding any extra information by being 0, right? So like the V complement.
Yeah.
Do you have to always go into an extra dimension?
No,
Like
so V is actually lives in R3. It's not
Oh,
the 2-dimensional. So it's not. So you don't have this setting. So this guy is, let's say, is living in a different space. I can use an R2. So this really is an R3, but it happens to just be contained to that plane. Okay. So usually you just fix the ambient space, ambiently R3. Every subspace is going to be there. And it's true that it doesn't add any information in the Z direction, but not all subspaces are like this. I can define more complicated subspaces, like, for example, let's say I have this vector and I don't know, this vector. Okay, what is this? This is going to be, let's say 1, 1, 0. That would be the first one, this one. And then 0, 1, 1. That's not going to work. No, that's not what I want. This should be, it's a little bit hard to draw. Okay, where is my? So imagine this vector, this one, that goes from 0 to 1, 1, 1. Okay. So one vector has all coordinates 1, the other one has the first two coordinates 1, the second 0. If you look at the span of these, this is a good point. You try to remember what the span is. The span is the set of all linear combinations of these two vectors. Okay, anyone can tell me what that span would look like? Yeah. It's not arching. I like carefully constructed it so that it's not arching. If you just move it a little bit, it would be arching. It's actually not, it can't be arching, sorry. It can't be arching because there are two vectors and they're at most. So okay. And that was so these are two. If they're linearly independent, at most they span a two-dimensional space. They can't span arching. The span arching you need at least 3 linearly independent. So this the span of this is at most two-dimensional. It could be one-dimensional, could be zero-dimensional, but are they linearly independent first? They are. So it's easy to see that they're linearly independent. Because if I do like C1 is plus C2 that, then setting equal to 0, C2 will be 0 because of this, and then C1 has to be 0. So linearly independent, so this is going to be a basis for whatever it spans. Okay, and that space will be 3 H. So what is that space? Yes.
The XY. Is the plane passing through the XY?
Yes, so if you imagine the xy, the line in which x is equal to y, and just extend it all the way in the z direction. So you can see if I do this, let's say if you do the span, it's very easy to see. I would get, let's say, C1, 110 plus C2, 111. So this would be C1 plus C2, C1 plus C2, and then C2. So you can see or argue for yourself that the two coordinates, the first two coordinates will always be the same. So they can't be different. And then the last coordinate can just be free. So what happens is you're going to have this x equal to y line. This is not good. A different color. So x equal to y line, and then you extend it in the z direction. So it would be this plane. So anything that's on this line, and then all the lines that are parallel to it in the z direction. Okay, so that's a subspace. It's a non-trivial subspace. Okay. And it happens to have an orthogonal complement. So any questions about this? This is a quick exercise for yourself to figure out. I give you two vectors, figure out the span, and then maybe describe what the span looks like. And it would be a linear subspace. It's two-dimensional. You can see, like, let's say, like a plane. And then linear algebra agrees because they're linear independent, and they form a basis. You could have taken different bases. So I could have taken, for example, this guy and this other guy. Okay. So these two would have been the same, like span the same subspace. It would have been easier. Right. I did it the hard way. So, and this will have an orthogonal complement. Anyone can imagine what the orthogonal complement would be?
Would it be all points on x equals negative one? Y equals negative x?
Y equal negative x. Yes, so that would be correct. So, like, if you want to figure out one vector that's orthogonal to this, would be, for example, 1, negative 1, 3. Right, so at least this line, yeah. So it's hard to maybe do this. So yeah, so if this is x equal to y, then so vector would be like 1, 1, 0 would be there, right? And I would need, for example, like 1, negative 1, 0 would be orthogonal to this, right? And this vector is also going to be orthogonal to the other one. So it's orthogonal to both elements that generate the space. So this vector, if I want to verify this vector, 1, negative 1, 0, is orthogonal to both. Maybe I should color it differently. This is going to be, I color it. Right. So that vector in this color would be 1, negative 1. So this is negative 1. So it would be like, it's a little bit hard to plot. So it would be this vector. So this is orthogonal to 1, 1, 0. And it's also orthogonal to 1, 1, 1. You can verify that because take the inner product of this one and the green one, and it will be 0. And it's hard to see on my drawing because just imagine this is gonna be that plane, and this vector is like this. The other vector is like that, and this. Let's see, this one and this one, and then the other one is just pointing in the other direction, which is like that. And so that is a particularly orthogonal vector. Once I found a vector which is orthogonal, any scale multiple of it would be also orthogonal. Okay, and this is describing as so what was your name by the way? Your name, yeah.
Aaron.
Aaron. As Aaron pointed out, this is going to be this line. Okay. So this line, everything on this line, x equals negative y would be, and then z is 0, would be orthogonal. To that plane, any more? Any other? It turns out that there is no other one, so it's just that line. So the orthogonal complement of this would be a line. And this is a general fact, so if the dimension of V is 2, the dimension of the orthogonal complement would be whatever adds up to give you the dimension of the full space. So this is two-dimensional. The orthogonal complement will have one dimension. The orthogonal complement of a plane would be a line. Okay. In R2. In a bigger space, it would be bigger. Does this kind of make sense? Everything that's orthogonal to this will lie in that line. Good. And it turns out, in the interest of time, I'm gonna not spend too much time on it, but this blue line is also in subspace, and it has an orthogonal complement itself. So what is the orthogonal complement of this blue line?
The plane.
Not which plane?
Purple.
The purple plane. So the purple plane would be the orthogonal complement of this. I mean, it's easier here. So this z-axis here is a subspace. The orthogonal complement would be the xy plane. Okay, so if you take the orthogonal complement the second time, you get back the original one. So start from V, take the orthogonal complement, you get a new subspace. And then take the orthogonal complement of that, you get back the original one. So it's a dual relation. Anyway, so this is the definition of an orthogonal complement. And I'm gonna skip this example because this is going to give you the same. So if you have X is like a matrix, look at the image of it, which is the span of these two vectors. The span of these two vectors is what? So what is the space? This is another example. This is the xy plane. So we're using a different basis here, but it's the same subspace. So the orthogonal complement will be the same. So it will be the z-axis. Okay, we already did it. And so no need to do it. So it doesn't matter which basis we use. The subspace is defined irrespective of the basis, and so you get the same answer. The new curve would be the same. So you can go through the argument here, but I'm not going to do it. And then the dimension of V and V curve is always going to add up to the dimension of the full space. So V is a plane, two-dimensional, V curve is one-dimensional, dimensions add up to 3. Okay, any questions? Now I want to move on to the most important thing here. So the projection. So if I have a subspace and I have another vector x, not necessarily on the subspace. So you have a subspace V and a vector x. I can define the projection to be the closest element in V to Z. Sorry, to X. So we have X. Say this is the XY plane. And then these are the axes. And then I have another vector which is not necessarily on the plane. This is X and this is V. So I'm gonna search. So this Z here is a dummy variable. So I'm gonna look at all possible Z's in V and then look at the distance of these two. So the distances are like at the difference basically between Z and X. So this is X minus Z, the norm of So this is, for example, this would be x minus c. And the norm would be just the length of this distance, the distance between the endpoints of x and z. So I'm going to look at different z's in the subspace and look at the distance. So here we're viewing vectors as points. So z's are going to be in v, and I'm going to look at the distance of x to z, which is measured in this norm. And arguing here means we're going to minimize it and take the argument that minimizes. So the z that minimizes this distance. So for example, this particular z is closer to x than this other z. You can see that purple line is longer. Okay, so I'm going to vary z until this distance is minimized, and then that z, whatever it is going to be called projection. And it turns out to be unique, so they're not two different things. There's just going to be one z that minimizes that distance. Okay, so that's called the projection of x onto v. It's the closest element in v to x. How do you measure closeness? Closeness you measure in the norm of the difference of the two vectors. Have people seen this before? Projection? So what do you know about the projection? How can you find the projection? What do we know about it? So imagine this is the plane, and this is my vector. So how do you find projection? Which vector would be the projection? Yeah, so you just you map this endpoint down perpendicular to the plane. So just drop it down. You can think of it as a shadow. If the light just shining from above, the shadow would be like the projection. Okay. So if I have something like this, and then that's my vector, then the projection would be I just drop this perpendicularly, and it could be like this. That would be x hat. That's the particular z that produces the smallest distance. Okay. What we need basically is this x minus x hat, which is the error. We call it error. It's just residual or error if you want. That vector, this is e, x minus x hat. This has to be orthogonal to v. Okay. Intuitively, it's clear. I mean, this is really not that vector because we discussed the vector has to come here because it has to start from this point. But I just like, it's easier to draw it there, but based on the point of and also that question, that's E. So this E is going to be perpendicular to V, but perpendicular doesn't matter. I mean, it's easier for you to this. You can view it as, this is the part that things get fuzzy. This is like really a vector, but it's also easy to draw it there, which is when you can see that x hat plus a gives you x. So this has to be orthogonal to v, which means that any vector in v I take, this error is going to be orthogonal to it. And this is the defining property. So you can prove that the x hat that achieves the smallest distance has this property that the error, we're calling it error, but the difference to x minus x hat is orthogonal to v. Okay. So, is this clear? Kind of. Geometrically, it's clear, but you can also prove it. So the error, x minus x hat satisfies E is perpendicular to V, right? So let me write it here. So E is perpendicular to V. So x is the projection, of x onto V, if and only if x hat minus or x minus x hat. This is orthogonal to V. Or if you remember what orthogonal complement means, E should belong to V perp. So if I project x onto V, I get some x hat such that the difference, which I'm calling the error, x minus x hat, is going to be in V perp. If that happens, then you have a prediction. Okay, so here you can see like the E is in the orthogonal complement. This is V perp. Sounds good. Sometimes called orthogonality principle. So to define a projection, we use the distance, but it turns out that in a linear space, the projection is characterized by this property that the area is orthogonal to the subspace. So we project x onto V, and we get a projection x hat such that the area, or E belongs to V perp. Okay. Questions? Yes.
What does argument mean?
Yes. So what it means is I'm going to minimize. So if you think of a function, let's say if we have a function fz that takes a vector and produces x minus z norm. Okay, so this function takes things in Rn to R. This is like a cost function. So you give me a z in Rn to calculate the distance. So I can define something like minimum of fz as z varies in V. So this is the smallest value that it takes. And then I can define argmin, which is the argument that gives me the minimum value. Okay. So for example, if we have like, let's say, in unit dimension, so fz would be, for example, x minus z. And let's say x happens to be, say d equal 1. 1, okay? So the minimum of fz would be, let's say z in all of Rn. The minimum would be, what will be the minimum? The minimum would be 0. And the argmin would be 1. Okay, this is like a simple example. It's the argument that they have. Any other question? Okay. So if you kind of understand, this is like a main topic in this course, and you will see it's a very interesting property in linear algebra. So once you understand this, note that I can write x as x hat plus e. You can think of x hat as being the best approximation of x in V. So if you think of V as representative of your knowledge, x is outside your knowledge, you want to represent it with what you know, the best we can do, the closest is x hat. Think of it as like an approximation or estimation. And then that's why I call error is what you can't represent. Your subspace, your knowledge is not sophisticated enough. It's like the component that's outside your knowledge. So E points in like a different dimension. Okay. So think of it like that. Then, I mean, by definition of E, if you rearrange, you can see x is equal to x hat plus E, because I define E to be x minus x hat. But this also can be viewed as a decomposition. So every vector has a decomposition like this. If you give me a subspace V, it decomposes every vector into a projection onto V and an error. So this belongs to V, this belongs to V perp. I can write every vector as a component, which is in V, plus a component which is in V perp. So this way, a subspace and its orthogonal complement decompose the space into two pieces. Two kind of interesting way of like the way the decomposition work is that I can write the vector as one piece from this and one piece from that, and this would be mu. For example, with the xy plane and the z, every vector would be like x1, x2, x3. would have this decomposition, x1, x2, 0, plus 0, 0, x3. So this would be the projection. It's easy to figure out that this is the projection onto the xy plane. This is the error. Okay, that corresponds to the case that the decomposition when V is the xy plane. But it's not limited to that case. For example, in this example, this subspace and its orthogonal complement decompose the space into the same fashion. So every vector has a projection onto this, and a projection, like an error along the perp, and that gives you the composition of the space. Okay. Does this kind of make sense? You can rewrite every vector as a component in V and V perp, and this holds for any subspace. So every subspace gives you a kind of decomposition like that, and so that's kind of this result that I kind of summarized here. Every vector in orientation uniquely, and it's going to be uniquely decomposed as two pieces, one in V, which is going to be projection, and the other in V perp, which is going to be perp. And we write R in A as like V, and then this circle plus V perp. This is like the abstract notation of linear algebra. So let's call it orthogonal direct sum. So Rm is orthogonal direct sum of V and V perp, which means that I can write every vector in there as a unique composition, two vectors, one in V and one in V. So this particular notation is not very important for us. I mean, if you end up like reading a more advanced linear algebra course and you run into something like this is what I mean. Question? This would be a sophisticated decomposition if the subspaces are non-trivial. It's not as obvious as X, Y, and Z, but it's much easier to see in the X, Y, and Z case. How many people have seen something like this before? Okay, a couple of people have seen it. So this summarizes the idea of projection and just ties it very nicely to orthogonal complement. And if you remember this, it's going to be very helpful. Again, this is the picture to remember. If you have a V and you have an X, you can project it onto V. That's going to be x hat. This is supposed to be orthogonal. So the error is going to be x minus x hat. It's going to be orthogonal to V. And you can think of the projection as the shadow of x onto V, which is shining the light directly on top. The error is perpendicular to the subspace. And also the length would be the shortest path from x to V. And this is like a kind of hint at what is to come. Like finding the regression coefficients, or like finding the least squares solution to the regression problem is exactly doing this projection. You're doing this projection onto V, which is the column space of the design matrix. And we'll see that. This is a proof that projection like is equivalent to like that error being orthogonal. It's up to you if you want to read it. It's optional. And yeah, anything else here that I wanted to? Okay. This is the summary. This one, the first one we have seen. So Rn can be decomposed into V plus V perp. It turns out, as I mentioned, dimension of V and dimension of V perp are equal to N, and V perp is equal to V. I mentioned that. The second fact, which is interesting, which we'll see, this is like the summary, like the algebraic summary of what regression is if you look at the matrix, it has a column span for an image, which is a linear subspace. So this is going to be RV. If I ask what is the perp of that V, it turns out that it's going to be the kernel of X transpose. Okay, and that's going to, we'll see it. And this relation, if you remember, is going to be the summarizing fact for regression. And this allows us to actually solve for the coefficient stuff. So we'll see that later in the course. So the most important subspace for us is the image of a matrix, or the column space of a matrix. And we want to ask the orthogonal complement because it turns out that then I can characterize the projection. Once I figure out the orthogonal complement of a solid space, I know that the error should be there, and then I write an equation and we can solve the projection. But the fact that image of X is perp to kernel of X transpose then means that if you apply this result, the dimension of solid space to the dimension of V perp is equal to the dimension of the whole space. If you apply it to this, you'd see that the dimension of the kernel of X transpose, which is the nullity of X transpose, would be plus the dimension of the image, which is the rank, is going to be equal to n. So if X is n by p. So that's the fact that I mentioned last time in the passing. So if you have matrix X, if you look at the rank, and then nullity of X transpose, then you would be some two n. The same goes for, I mean, this you can invert as well. So image of X transpose, when you replace X with X transpose, there's a dual version of this. But this fact, this is like A plus B. So A plus B gives me this fact, which is not as important for us as much. I mean, once we remember this, and this will see, because this is the most important. Any question? Has anyone seen this identity? One else? Just one. You didn't see this in the algebra? Maybe like column space or something? Okay, no one else. Okay, we'll see. Okay, so this is what I want to talk about, like tell you about projection at this point. We'll come back to this many times and we'll see this picture many different times. The top part we discussed today, the second part we'll discuss later. And then third part is good to remember for yourself. Any questions about this? All good? This is the end of projection. Good to ask questions if it wasn't clear. If not, we're gonna we have 15 minutes to go through the rest, which is a very important topic in algebra, and it deserves like a couple of lectures on its own. But in the interest of time, we're just gonna do 15 minutes, actually 7 minutes or so, and then two different things about matrices. So we're gonna talk about properties of symmetric matrices. So if you have a matrix which is square, this is going to be about the square matrices, n by n. Let's say A is n by n. It's symmetric, so A is equal to A transpose. There is this thing called, so you know what the symmetric matrix is, right? Symmetric matrix. 1, 2, 3, 4. Is this symmetric? No. How can I make it symmetric? So the diagonals should be off diagonal elements should be the same. The diagonal, so A and the transpose should be the same. So if the matrix is symmetric and real value, then it has a what we call so-called eigenvalue decomposition. Okay, or EVD. So A can be written as a decomposition into the product of three matrices: the matrix U, the matrix lambda, and the matrix U transpose. So the last one is the transpose of the first one, with a special property. So U will be an orthogonal matrix, or an orthogonal operator, if you remember matrices are operator. Orthogonal means U transpose and U transpose U are both equal to I. So these are going to be all n by n. So n by n. So all the matrices involved are n by n. I'm not going to write it. So this has this property that U transpose plus and U transpose U is identity, and lambda will be diagonal, and the elements are, let's call this like lambda 1 up to lambda n. This is my notation for a diagonal matrix which has these entries on the diagonal and zeros elsewhere. So lambda would be a diagonal matrix. Okay. And the fact is, what this orthogonality means is if I write U as the set of its columns, sorry, or just decompose it into its columns. Let's say U1 is the first column, U2 is the second column, and UN is the last column. What this relation means It's actually what this one means. The second one. So if you write it down, so U transpose U would be that this is like a block decomposition of a matrix. This is like n by 1. I can do a block transpose. So I get U1 transpose. This would look like this, U2 transpose, and UN transpose. And then I multiply it by U, U1, U2, UN. This is like a block matrix multiplication. It's not like the usual. So this is like 1 by n. This is n by 1. But I can multiply it because they match as if I'm doing the like the scalar multiplication. U1 transpose U1 would be the first element. U1 transpose this one times this would be the second element. Up to U1 transpose UN would be the last element of this slide. And then you go like the second one gives you the second row. U transpose U1, U transpose U2. And so on up to UN transpose U1 and then UN transpose UN. Okay, so this matrix would be like this. And you can see that these elements are inner products of the columns of U. You remember, this is how you represented inner product. So this is, for example, U1 inner product with U2. And this matrix being equal to identity means all the off-diagonal elements are 0. So what it means is that UI is orthogonal to UJ if I is not equal to J. Okay, so everything here, these are all 0. Okay, and the diagonals are going to be 1 because it's equal to identity. So the inner product of every vector here with itself, which happens to be its norm squared, would be 1. Okay, so diagonals being equal to 1 means the norm is 1, and the off diagonal means they're perpendicular. So these vectors have unit norm, because the square is 1, the norm itself is 1, the norm is positive. So they have unit norm and they're pairwise orthogonal. Okay, that's what orthogonality means, and this relation means. The other relation you transpose, you can verify, means just the rows are pairwise orthogonal and orthonormalism. Like sorry, normalized as well. But one is enough. So once you have it from linear algebra, U is going to be in the inverse of U transpose, so the other one is going to be automatically true. So for us, this version is more important. U transpose U is equal to identity. And if you expand, we do want to expand. So okay, so let's not expand. So this is the meaning. And it turns out that in this decomposition, what these U's are going to be the eigenvectors of the matrix. Okay, and lambdas would correspond to the eigenvalues. So what would happen is these UIs and the lambda i's are eigenpairs of A. So this would be an eigenvalue, and this would be an eigenvector. So how many people remember what eigenvalues and eigenvalues? No one remembers. That's great. No one remembers what eigenvalues are. Like half the algebra is what eigenvalue. Okay. The other half is like linear systems and stuff. Okay, so you know what? You can verify what so I'm telling you that these are the eigenvalues. So each matrix, like symmetric matrix, has what's called like a set of eigenvalues. And so what is an eigenvalue? Lambda is an eigenvalue of A if there exists another vector, there exists U vector such that A times U is lambda U. Okay, whenever I multiply A by U, or yeah, form AU, it would be lambda U. Okay, lambda is a scalar, so in R. So if you remember what I mentioned about the matrices being operators, remember that matrices are operators. So this is telling you how a matrix operates on a vector. So that particular U remains kind of in the same direction because the input and output domain of A are the same. It's a square matrix. So AU is how A transforms U. Because the input and output is the same, it's just maps it back to the same space, and it happens to be mapping it back in the same direction. It's just scaled by a factor. Lambda could be like 1, or it could be -2, or just a scalar, but in the same direction, because lambda U is just scaling U. Okay. So if you just end up, for example, in R2, if you're here, sorry. It could be like this vector is an eigenvector. If I apply A to it, it might end up being like this, maybe -1/2 U. That's fine. It may end up being this, it may end up being that. But if I apply it to and I get something like this, that can be an eigen. It has to be in the same direction. And it turns out that any vector in that direction will also be an eigen. But these values would be distinct. And for a symmetric matrices, we'll have exactly n distinct, they're not actually distinct, but n eigenvalues. And then for corresponding to everyone, I can find at least one vector which is non-zero, because 0 would always satisfy this. U has to be non-zero. And those will turn out to be these pairs. So I would have like like ui is equal to lambda I. Ui, I from 1 to n. So we'll have exactly, well, we can find exactly n eigenvalues and n eigenvectors. These are not unique, but I'm normalizing them. Once you normalize, they're going to be unique. So they're going to be normalized to unique norm. And it turns out that for symmetric matrices, I can make them all these pairwise orthogonal. So I do the eigendecomposition, I find the eigenvectors and eigenvalues. I make sure that the eigenvectors are normalized to unique norm and they're orthogonal. Then I'll have that decomposition. I can form the U, and then I can form lambda. And this is just summarizing everything there. Okay, so the way that U is constructed and lambda constructed are from the eigenvalues and eigenvectors. Okay. And in fact, if I give you a decomposition like this and tell you that U is orthogonal and lambda is diagonal like that, you can prove that these are the eigenvalues and the columns are eigenvectors. All you have to verify is this identity, which you can do. So you can just multiply A by UI and just replace A with U lambda U transpose and do the multiplication. And you end up proving that the other side is lambda UI. Okay. This is a little bit tough if you don't remember what eigenvalues and eigenvectors are. Is this sort of clear? So I'm going to ask maybe the TA to go over eigenvalues and eigenvectors a little bit more. And the main thing is to remember this decomposition. Okay, like we want to abstract decomposition. I'm going to ask you to also do it maybe homework here to verify, like, to remember what eigenvalues are. But the abstract thing is very easy to remember. So every symmetric matrix has a decomposition. It's like a 3-factor decomposition involving 2 matrices. One, an orthogonal matrix, which is the special property that all the columns are orthogonal, and also unique norm. So this is called orthonormal. So the columns are orthonormal. And the middle thing is a diagonal matrix. And then U transpose and transpose of U. So this decomposition is very useful. Once you have this, because of this special property, a lot of things simplify as this. Rather than working with A, you can work with these. There's a lot I can say about this, but I think that's good enough. And I'm going to give you, so this is just summarizing what I mentioned. So these are the eigenvectors, and eigenvectors are the columns of U, and then the diagonal elements on the lambda are the eigenvalues, and the eigenvectors of the columns are either, like the inner product is either 1 or 0. If they're the same, it just tells you that the norm is 1. If they're different, it just tells that the different columns are orthogonal. So this would form an orthonormal basis. So this will be a basis for Rn. If you remember, I told you that if you have a set of vectors that are pairwise orthogonal, and none of them is zero, it would be linearly independent. So they're going to be linearly independent because of the pairwise orthogonality, and because there are n of them, and the dimensional Rn is n, they would form a basis. They have the same, the right amount of ones. So they form an orthogonal basis Rn. So every symmetric matrix gives you this canonical orthonormal basis of the space. Forget about the SVD. I'm going to give you an example to see. It looks like, so for example, if you have 1, 2, 2, 1, okay, you calculate the eigenvalues. It turns out that eigenvalues of this matrix are 3 and -1. Once you review what eigenvalues and eigenvectors are, then you would be fine, but I mean, you can easily verify. The key is that this is going to be the eigenvector associated with that, and this is going to be the eigenvector associated with this. I can easily verify that by, for example, the claim is that the second column, the first column, like 1 root 2, 1 root 2 is an eigen vector of A. So if I multiply, I get 3 times 1 over root 2. And the other one gives me 3, 1 over root 2. So I get 3 times 1 over root 2, 1 over root 2. So if this is U1, this is A, I get back something in the direction of U1, but multiplied by 3. So that would be the note. So this is proof that 3 is an eigenvalue corresponding to the eigenvector U1, and you can do the same for the second one. If I multiply this by the second column, I get -1 times the second. And then we found 2 eigenvalues. There's a better way to find the eigenvalues. Like I'm telling you the eigenvalues is, and the eigenvector is very easy to verify, but how to actually find it from this matrix? You're going to review your unique algebra problem. It's not that important for us in this course. But once I have it, once I have the 2 eigenvalues and the 2 eigenvectors, I can form, this is going to be U1, U1, sorry, U1, U2, and this is just a transpose of that. So this is just U transpose, and then the matrix in the middle is the diagonal matrix of the eigenvalue. And then if you multiply out these 3 matrices, you can easily verify that it should match this. So I managed to write A in this form. This particular form is what matters. Okay. And then you can also verify if I multiply U by U transpose, it's going to be identical. So you can see that if you take the norm of the first column would be 1, the norm of the second column would be 1, and the inner product of the 2 would be 0. Just do the multiplication. Here's another one. So if I have a matrix like this, you do the same. It will have an eigenvalue 2, an eigenvalue 0, and this vector is going to be corresponding. This is the first eigenvector corresponding to this eigenvalue. This is the second eigenvector corresponding to, not this one, the diagonal entry. So the eigenvalue could be 0, it's fine. And we'll end up having this form. We'll still have this form. The interesting thing is, this guy in the middle tells you a lot about the matrix. Also, U also tells you a lot. So the fact that, for example, this eigenvalue is 0 tells you about the rank of the matrix. So what is the rank of this? 1. Why is the rank 1? Because the columns are like multiple of each other. So if you take like you want a basis for the column span, you can just take one of them at most. And so the fact that this rank of this is 1, it's not full rank, is reflecting the fact that one of the eigenvalues is 0. So the number of 0 eigenvalues tell you like something about the rank. If the rank is the dimension of the matrix minus the number of 0 eigenvalues. So the rank is 1 because there's 1 non-zero eigenvalue. How about the rank of the top one? 2, and you can see the eigenvalue. Okay, so this the composition already tell you. It's easy to figure out. Basically, the rank of this would be the same as the rank of the middle. So these won't change the rank. So the rank of this is easy to see is 1 because one of them is 0. The rank of the other one is 2. Okay. Question? It's like a 2-slide summary of what would take a book to talk about. Okay. But the last thing we did not. So the last thing that we want to talk about is positive semi-definiteness, which is going to be maybe next time, like 2 slides on this. Any questions? Okay, thank you guys.